Hello everybody. Now we shall discuss about determination of hysteresis loop. Determination of hysteresis loop. Before going to discuss about determination of hysteresis loop, let us discuss about BH characteristics. First, let us discuss about BH characteristics. What is BH characteristic? Okay. BH characteristic or BH curve or BH curve. It is the curve which gives the relationship between B versus H. What is B? You know, B is flux density, which is equal to flux per area. What is H? H is magnetic intensity, which is equal to Ni by L. H is equal to Ni by L, whereas B is equal to flux per area. Okay. Um, in free space, in free space, or in air, in air, what is this curve? What will be this curve? BH curve will be linear. BH curve will be linear. In free space or in air, the BH curve is linear because B is equal to mu into H, which is equal to mu naught mu r H. In case of air, in air, mu r will be equal to 1. Then B will be equal to mu naught into H, where mu naught is constant, proportional constant. Then B is directly proportional to H. That's why in air or in free space, the BH curve will be linear. The BH curve will be linear. If you take any other, if you take any magnetic material, the curve will not be like this. The curve will not be linear like this. Coming to the BH curve, in case of any magnetic material, first let us take one magnetic material. Let this is one magnetic material. In any magnetic material, a very large number of tiny magnets are present. In any magnetic material, a very large number of tiny magnets are present. You're going to have a very large number of tiny magnets are present inside of this magnetic material. In any magnetic material, a very large number of tiny magnets. These tiny magnets are called magnetic dipoles. Simply, you can call it as dipoles. All are dipoles. Very large number of dipoles are present inside of this magnetic material. In any magnetic material, very large number of tiny magnets are present. Those tiny magnets are called magnetic dipoles. These dipoles are distributed randomly. Okay, before the metal has been magnetized, this is in the absence of external magnetic field. In the absence of external magnetic field, all magnetic domains present in this magnetic material are distributed randomly like this. Okay, so you're going to have north pole, south pole, all are tiny magnets, north, south, north, south, south, north, north, south, north, south, north, south, north, south, all are having poles, dipoles, all are dipoles, north, south, like this, all are distributed randomly, north, south, like this. Okay, before the material before the material has been magnetized, material has been magnetized, that is, in the absence of in the absence of external magnetic field, external magnetic field, in the absence of external magnetic field, you're going to have randomly distributed magnetic domains, magnetic dipoles present in magnetic material. Okay, so here the net magnetic field will be zero. As all are distributed randomly, the net magnetic field will be zero. After the metal has been magnetized, let us do one thing. You take some magnetic material and winding is wound upon this magnetic material. Okay, you apply some external magnetic field, you apply some voltage to this. Okay, then after the metal has been magnetized, all dipoles will get aligned themselves in one particular direction. That is, all all domains present in magnetic material align themselves in one particular direction. Okay, here all domains, all magnetic domains aligned aligned themselves in the direction of in one particular direction, or in the direction of applied force, in the direction of applied force. Okay, so this is the situation after the metal has been magnetized. Okay, so after the metal has been magnetized, after the material has been magnetized, all domains will get aligned themselves in one particular direction. All domains will get aligned themselves in one particular direction. Okay, so magnetic field will be produced. Sorry. Okay, sorry. Magnetic field will be produced. Okay. Okay, after applying some external force, external magnetic force to this magnetic material, okay, all domains will get aligned themselves in one particular direction like this. If you stop providing this voltage, external magnetic force, then again they'll come back to their original positions. Okay, after removing the supply, okay, again they'll come back to their original positions. As long as the external source is present, external magnetic force is present, these domains will get aligned themselves in one particular direction like this. After removal of supply, okay, after the removal of external field, external force, again they'll come back to their original positions. Again they'll come back to, these domains will come back to their original positions. Okay, so the very first point is, in any magnetic material, a very large number of tiny magnets are present. Those tiny magnets are called dipoles, magnetic dipoles or magnetic domains. Okay, so before the metal has been magnetized, in the absence of external magnetic field, these domains are distributed randomly like this. You're going to have randomly distributed domains in the magnetic material in the presence of, sorry, in the absence of external magnetic field. In the absence of external magnetic field, these domains are distributed randomly like this. You're going to have randomly distributed magnetic domains. Now let me apply some force, magnetic force, to this magnetic material. Okay, then these domains will start aligning themselves in one particular direction. After the metal has been magnetized, all domains will get aligned themselves in one particular direction, in the direction of applied force. When you remove the supply, as long as the supply is present, as long as the supply is given to this magnetic material, you're going to get the flux. When you remove the external force, again these domains will come back to their original positions like this. Again they'll get distributed randomly like this. Again the net magnetic field will be 0. Here this is not equal to 0. Net magnetic field is not equal to 0. It is some finite value. Okay. Now let us discuss about a BH curve. Experimental determination of BH curve. Okay, supply is given to this magnetic material. Here we use flux meter. You can also use ballistic galvanometer for the measurement of flux. It is not only used for the measurement of charge, it can also be used for the measurement of flux. Okay, so here n is equal to number of turns, L is equal to mean length, of the flux path, of the flux path mean length of the flux path, where A is cross sectional area, cross sectional area. And reading of flux meter is flux, reading of ammeter is I. Okay, you know H is equal to Ni by L, and B is equal to flux per area. Okay, now let us draw the BH curve for this magnetic material. Okay, this is flux B, flux density B is equal to flux per area. H is equal to Ni by L. Okay, actually it is ampere turns per meter. Okay, now here you can see here this BH curve operates in three regions. BH curve operates in three regions: linear region, non-linear region, saturation region. Okay, you're going to have three regions. It operates in case of air, it is linear, but in case of magnetic material, it is not like this. The relationship between B and H is not like this in case of magnetic material. Okay, so now coming to this, this BH curve operates in three regions. First, it operates in linear region. The initial portion of BH curve is nearly a straight line. It is almost linear. This curve, the initial portion of BH curve is nearly linear, and the zone in which the BH curve is operated is called linear zone. That's why it is called linear zone. It is almost linear, It is almost straight line. Okay, so the initial portion of BH curve is almost straight line. Okay, now after this point, it deviates from linear relationship. BH curve starts deviating from linear relationship and enters into non-linear region, non-linear zone, and enters into non-linear zone. Okay, this is non-linear zone. Okay, after this point, finally you're going to have saturation region. Finally you're going to have saturation region. Okay, coming to the observation here, with the increase in current, you know H is equal to Ni by L. Okay, so with the increase in current, flux will be increasing. Okay, see how can you increase this magnetic field intensity? With the increase in current, you can increase H. Okay, so if this is increasing means B will be increasing. Okay, so at starting the curve is almost linear, not exactly linear, almost linear, almost linear, almost linear like this. Okay, after this zone, curve is deviating from its linear relationship. Okay, curve is deviating from its linear relationship. Okay, then after you're going to have saturation region. Okay, this is what non-linear zone, this is linear zone and saturation region, saturation region, saturation region. Okay, with the increase in current, flux will be increasing, or with the increase in H, magnetizing force, flux density is increasing in this region. Okay, so here rate of rise in flux density is more, delta BH is more in this region, whereas in this region delta B2 is, in this region delta B1 is rise in flux density. Okay, whereas in this region rise in flux density is delta B2. Okay, the slope of, in this region, dB by dH is more, and the slope is gradually decreasing. Okay, dB by dH is less in this region. In this region dB by rate of change in flux density with respect to magnetic intensity is almost, it is very less, very less, very less. Okay, so here see delta H, from here to here is delta H, again from here to here is delta H. For the same value of delta H, you compare these two regions. In these two regions, for the same value of delta H, for the same value of delta H, delta B1 is greater than delta B2. Okay, this in this region, with the increase in H, with the increase in H, B will be increasing, B will be increasing, almost maintaining linear relationship. Coming to this region, even though you increase H, there is no much increase in B. Even though you increase H, there is no much increase in B. Coming to saturation region, even though there is very much increase in H, even though there is very much increase in H, there is small, very small increase in B, almost negligible. Okay, at this point we can say it is saturation point. Okay, the material is saturated at this point, means even though you try to increase H, even though you increase more, if you increase more current, even though you try to increase more current, this will not get increased, this will not increase, this B will not increase. Okay, why it is happening, why this is happening, why it is almost maintaining linear relationship, then after non-linear relationship, then after saturation region, why it is happening? Because okay, now here see, as we discussed earlier, before the material has been magnetized, all domains are distributed randomly like this before the material has been magnetized, right? Okay, at this point you're going to have distribution of domains like this. Okay, okay, now before the material has been magnetized, all domains are distributed randomly like this. Okay, now in the initial portion of this curve, it's starting with the increase in H, B is increasing linearly, almost linearly, due to the presence of more number of randomly distributed domains. Due to the presence of more number of randomly distributed domains, This B increases with the increase in H almost linearly. Okay, you do one thing. For example, you take 1,000 domains. Okay, practically uh, very large, very large number of domains are present in magnetic material. But for example, let us let us take 1,000 domains. Okay, 1,000 domains are present in this magnetic material. 1,000 domains are present in this magnetic material. Okay, so in this region, you do one thing. In this region, as initially at starting, more number of almost 1,000 domains are present for alignment. Okay, more number of randomly distributed domains are present, right? Okay, so there will be scope of uh, alignment of more number of dipoles. So almost you take 700 domains will get aligned themselves in one particular direction. Almost most of the domains will get aligned themselves in one particular direction. Okay, so in this region, the almost 700 domains will get aligned themselves in one particular direction. Okay, with the application of magnetizing force, these domains will start aligning themselves in one particular direction. Okay, so in this region, almost 700, almost most of the domains will get aligned themselves in one particular direction. Very some domains are left over for alignment. Okay, some domains are still randomly distributed domains. Okay, in this region. Okay, so out of 1,000, almost 700 domains got aligned themselves in one particular direction. Okay, so how many left? 300 left. Okay, now you do one thing. Now when coming to this region, non-linear region, 250 domains will get aligned themselves in one particular direction. Okay, coming to this region, okay, only few are left. Only few are left for alignment. Only few are left for alignment. Almost 50 are left for alignment. Okay, so only 50 are left for alignment, right? Okay, so here most of the domains will get aligned themselves in one particular direction. Net magnetic field will be more. With the increase in magnetizing force, net magnetic field will be increasing. Magnetic field will be increasing due to the availability of more number of randomly distributed domains. Okay, that's why it is almost linear. Rate of alignment is more. Rate of alignment is more means more magnetic field will be produced. More magnetic field will be produced. Okay, coming to this region, only some domains are present for alignment. So rate of alignment, rate of alignment of randomly distributed domains is less in this region. Rate of alignment is less. Rate of alignment is less. Whereas in this region, rate of alignment of magnetic domains is more. Whereas in this region, rate of alignment of magnetic domains is less when compared to this. That's why it is entering into non-linear region. That's why with the same value of delta H, delta B1 is greater than delta B2. Okay, for the same value of delta H, there is much change in delta B1, there is less change in delta B2 due to the presence of less uh, randomly distributed, less number of randomly distributed domains, as most of the domains will get aligned themselves in this region. They'll get aligned themselves in one particular direction in this region. Okay, only some domains will left over for the alignment. So rate of alignment will be less in this region when compared to this region. Coming to this region, almost all dipoles will get aligned themselves in one particular direction in both regions. Okay, only very few are left over for the alignment. So even though you increase in this region, due to the presence of very less number of randomly distributed domains, very less number of randomly distributed domains, even though you increase h, even though you increase h, there is no increase in h, there is no much increase in b. Even though you increase h in this region, there is no much increase in b. There will be very less increase in b with the with more increase in h. Okay, now the material is saturated. Okay, that's why this material this BH curve operates in three regions. That's why the BH curve, the relationship between B and H will be like this in any magnetic material. Okay, now coming to the determination of BH curve, determination of hysteresis loop. Okay, now you're going to have hysteresis loop. Okay, B versus H, where H is equal to Ni by L, where B is equal to flux per area, right? Okay, now you know, with the increase in current, here you are applying voltage to this magnetic material. With the increase in current, okay, with the help of this resistance, you can increase or decrease the current, right? So with the increase in current, H will be increasing, means indirectly, I mean, if you increase current means you are increasing magnetizing force H, right? So with the increase in, if current is zero, B will be 0. With the increase in current, okay, B will be increasing like this. And anyhow, you know, sorry, okay, fine now. Okay, this will be BH curve, right? Okay, so let this is O, this is point A. Okay, now the material is saturated. Okay, here you are going to get plus B maximum, B maximum. Okay, at this point, even though you increase H, B will not increase. Okay, when current is 0, H will be 0, then B will be 0. As H is increased, B also increases like this. Okay, and it operates in three regions: linear, non-linear, saturation region, like this, right? And finally this curve reaches its maximum value plus B maximum. This point is maximum value. Beyond this point, even though you increase this H, B will not increase. Okay, you know the reason, right? Almost all domains will get aligned themselves in one particular direction at this point of time. So no domains are present for alignment. So even though you increase H, B will not increase. It reaches its maximum value at this point, right? Okay. Now what you do is, now it is following the path OA, right? This curve is following the path OA, right? Now what you do is, now you decrease the current. with the help of this resistance, now you decrease the current. You decrease the current. If you decrease the current, the curve will be like this. Okay, fine. Point A, and let this is point B. Okay, now you are decreasing current. Now you are decreasing current. See, you have increased till this point. Now you are decreasing the current. If you decrease the current, B will be decreasing. B will be decreasing, but this curve doesn't follow the same path. While increasing, it is following the path OA, but while decreasing, it is a following path. It is following the path AB. It doesn't follow the same path while decreasing the current. Okay, B will be decreasing like this, which is this curve is following this path. Okay, at point B, okay, so at point B, the magnetizing force H is 0. The magnetizing force H is 0. H is 0, but H is 0, but B is not 0. B is not equal to 0. Even though H is 0, B is not equal to 0. And B is equal to, sorry, B is equal to OB. B is equal to OB. That is, the magnetic flux density in the material has a finite value. It has finite value. It is not equal to 0. Even though, see, even though the magnetizing force is 0, B is not equal to 0 here. Why it is not equal to 0? Here H is 0, right? If H is 0, even though H is 0, B will not be equal to 0, because see here, see. H is 0 means current is 0. Okay, first we took some magnetic material. Randomly distributed domains are present in this magnetic material, right? Randomly distributed domains. Then after you are magnetizing this material, you are applying some external force. This will get magnetized like this. So all domains will get aligned themselves in one particular direction. Reaching its maximum value means B max. All domains will get aligned themselves in one particular direction. Okay. Here randomly distributed domains. Okay. Aligned. All domains aligned themselves in one particular direction. All domains will get aligned themselves in one particular direction. That is, the metal has been magnetized now. This is before the metal has been magnetized. All domains are distributed randomly. Okay, B max. After the metal has been magnetized, all domains will get aligned themselves in one particular direction. Right? Okay. Randomly distributed. Now, if you remove the supply, again these domains regain their original positions. They'll come back to their original positions, means again they'll get distributed randomly, but suddenly all of a sudden, even though you make current 0, all of a sudden they'll not come back to their original positions like this. Again they'll come back to their original positions like this. After the metal has been magnetized, these domains will get aligned themselves in one particular direction like this. Okay, if you remove the supply, again these domains will come back to their original positions. Again they'll come back to their original positions. Again they should distribute it randomly like this. Okay, but all of a sudden all domains will not get distributed randomly. Few aligned domains are present. Okay, still few domains are present. Few aligned domains are present. Okay, aligned domains. These are randomly distributed domains. Few aligned domains are present. Okay, they similarly, all of a sudden they'll not come back to their original positions, even though the current is 0. Still, some domains are some aligned domains are present here. Because of these domains, magnetic field is not zero. Okay. Now you do one thing. You increase the current in reverse direction to make B zero. So now you are now you are increasing current in reverse direction. Current in reverse direction. You increase the current in reverse direction, okay, to make B zero. Okay, now at this point, at point C, flux will be equal to zero. Flux becomes zero. Okay, so at point B, even though the magnetizing force is zero, but B will not be equal to zero because of this reason. Okay, even though the current is zero, still some aligned domains are present in this magnetic material. All of a sudden, all domains will not regain their original positions like this. Okay, because of those domains, magnetic field is present. Okay, that magnetic field, okay, that OB, this is called residual residual magnetic flux density. Residual magnetic flux density. Okay, now you do one thing. In order to make this B as zero, you increase the current in reverse direction. Start increasing current in reverse direction. Okay, you increase the current in reverse direction. Okay, now you can make B zero at point C. So at point C, B is zero. B is zero, but H is not zero. Okay, at point C, H is equal to OC. Okay, now at point C, B is 0, H is equal to OC, right? So again, still you increase the current in reverse direction. How can you increase the current in reverse direction? By using this reversal switch. By using this reversal switch, you can increase current in forward direction, or you can increase current in reverse direction. You can increase or decrease the current in forward or reverse direction by using this reversal switch. Okay, so still if we increase the current in reverse direction, it reaches negative maximum. Okay, this point is D. This point is D. Okay, that is minus B maximum. Minus B maximum. It, okay, in reverse direction, the material is saturated. In reverse direction, in forward direction, the material is saturated. In the reverse direction, the material is saturated here. Okay, now you do one thing. Now again you increase the current in forward direction, then this will be increasing and traces one complete loop like this. So this is point E, this is point F. Okay, this follows the path. Okay, so A, B, C, D, E, F, G. Sorry, A, B, C, D, E, F, right? Okay, now here at point B, at point B, at point B, even though the H is 0, B is not equal to 0, and where B is equal to OB. Okay, this is called residual flux density. Flux density. Okay, in other words, B lags H, because even though the H is 0, B is not equal to 0. This is lagging behind H. Okay, so the greater the lag, the greater is the residual magnetism. The greater the lag, the greater is the residual magnetism. Okay. Here we have one definition. The power of the power of retaining the power of the power of retaining the power of retaining residual residual magnetism residual magnetism is called retentivity retentivity of the material retentivity 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 of the material. Okay, the property of holding this magnetism even though the magnetizing force is zero is called retentivity. Okay, and now at point C at point C at point C B0 H is not H is equal to OC. Let this is O point O OC. Okay, what is the meaning of this? Okay, so this much negative magnetizing force is required to make B0. Okay, that is the value of H, that is which is equal to OC. H is equal to OC is equal to OC. This much value is required to wipe out the residual magnetism. The value of H required to wipe out the residual magnetism residual magnetism magnetism is called as coercive force is called coercive force coercive force. Okay, that is HC is coercive force. Okay, so now with the increase in current in reverse direction and it reaches negative B maximum. Okay, again if you increase current in forward direction, again it will be increasing like this. It follows the path DEF A. Okay, you are going to get one complete loop. Okay, now you can apply DC voltage like this and you can have the curve like this. Okay, if we have AC voltage, if we apply one cycle, if one cycle of AC voltage given to magnetic material, you're going to get one complete loop like this. Sorry. You're going to get one complete loop like this. Okay. Okay, one complete loop like this. Okay. The thickness of this loop is depending upon the material. Okay. one cycle you're going to get one hysteresis loop like this. Okay, if the iron piece is subjected to one cycle of matization, if matic material is subjected to one cycle of matization, you're going to get one hysteresis loop like this. Okay, so if you use 50 edges supply, okay, that is 50 cycles per second, right? Okay, then 50 loops will be formed. For one cycle, one hysteresis loop will be formed. For 50 cycles, okay, 50 hysteresis loops will be formed. 50 hedges, 50 hedges means 50 cycles per second. Okay, so for every second, for uh, for every second 50 loops will be formed. Loops will be formed. Okay, for one cycle you are going to get one hysteresis loop. Okay, hysteresis loss is depending upon this thickness of hysteresis loop. Okay, so here we use ballistic galvanometer for the measurement of flux. You can also use flux meter. Okay, this can be used to uh, increase or decrease the current in forward or reverse direction. This is what reversal switch. Okay, thank you.